Hello, it's Dr. Daystorms. And in this section of Chapter 6, we're going to be discussing quantum numbers and how to use them with respect to quantum mechanics. And I know the physicists out there will really hate the way that, or think that I'm oversimplifying it, and I am in a way, but you can think of quantum numbers as being like an electron social security number, or almost like their address. First, I want to discuss a little bit about Heisenberg. And what Heisenberg came up with was this idea that you can, if you know the momentum of a particle, then that puts a limit on knowing its exact location. And so this portion of the equation here is momentum, which is mass times velocity. And so if there's a change in the momentum of something, then that puts a limit on the known position. And so I would never ask you to really solve this equation because there's complex math behind it. But what this means is that since we have an idea of the mass of an electron and an idea of how fast it's going, it makes it it's impossible to know its exact location. In fact, if you solve this equation mathematically, it's bigger than the size of an actual atom. And so we just cannot know its exact location because of this limitation. It's called Heisenberg uncertainty principle. So most cases, we're talking about the whereabouts of the electron is greater than the actual size of the atom, is what I was trying to get at, since it's such a small mass and it travels so quickly. Next came along Erwin Schrödinger, and Schrödinger really started to develop this idea of trying to come up with an idea of the location of where the electron would actually reside. And he went through a very, very complex set of mathematical equations, which I would never ask you to memorize or to be able to differentiate. However, what he did was he came up and he wanted to incorporate both the matter nature of an electron along with its wave nature. And so by putting both of these into this equation, he came up with what's called a wave function. Okay, this leads to the field of known as quantum mechanics. So this wave function or wave equation is designated with a lowercase Greek psi. And what's interesting about it is if you square that, so you square the wave equation, it's going to give you the probability map, the density map of where the electron most likely could be at any given time. And you've probably seen density maps with respect to like population density or some of the other fields. And this is very similar to that in the sense that this means that there's a high order of probability that there's an electron that's residing in this section, in that area. We just don't know exactly where because of the fact that there's the Heisenberg uncertainty principle and that limits are to know the exact location. So if you solve for the wave equation, you get a set of wave functions, which, rather than call them wave functions, and this is where the electron lives or resides, we like to use the term orbitals. Okay? And these orbitals all have corresponding energies, which is what we've been discussing earlier, and how each energy level is equal to, E is equal to Planck's constant, h, times nu, the frequency. Okay? So each of these orbitals describe the spatial distribution of the electron density or the probability of finding an electron in that location at any given time. And these orbitals are described by a set of 3 quantum numbers. Now, I want to stress something here. There are technically 4 quantum numbers. You have 4 quantum numbers. It's just that the first 3 describe the orbital in which the electron lives or resides, and then the 4th one is the one that talks about the electron's magnetic spin specifically. And so that's why technically there are 4 quantum numbers, but the first 3 describes the orbital. The 4th one is the one that differentiates the electron from its neighboring electron. So let's first start off with the principal quantum number, and as we mentioned in class, these are denoted with a letter. So this one is a lowercase letter n. This is the principal quantum number. N is always going to be an integer. And remember, an integer is a whole number. So the principal quantum number describes the energy level on which that orbital resides. Okay, so where's that orbital? What energy level is the orbital on or in is the n number, and then the values are always greater than or equal to 0. Oops. And once again, you probably learned, like in or in high school, the whole idea of where you draw the energy levels, where you have the nucleus, we have the first ring, the first orbital, and the second ring was the second orbital, third ring was the third orbital, and this would be, for example, n equals 1, n equals 2, and then n equals 3. We're going to find out that that's an oversimplification, but the principal quantum number really does describe which energy level has that orbital. The second quantum number is the angular momentum, and that's what I'm going to always call it, is angular momentum. Some of the older books, or if you have an older text, or some of the other texts may call it azimuthal, but that means the same thing. But we're talking now about the angular momentum quantum number, and what's really cool about this one is it tells you the shape of the orbital. So unlike what you probably learned in high school, not all of the orbitals are going to be round. Okay, we're going to find out there are types of orbitals that are round, but not every single one will be round. And so the way that you can find out what shape the orbital is based off of its angular momentum quantum number, and its lowercase l is its symbol. L is also always going to be an integer, and it ranges from 0 to n-1. So I like to write this out mathematically, to where we say that L, oops, here, let me give myself more room, L has to be between 0 and n-1. So for example, if n equals 3, then L can equal 0, 1, and 2. Whoops. 2. So there are 3 possible L values. And so what do these numbers really indicate? And like, what does it tell you? Like, what's the shape of an L equals 0? Okay? Well, I want you to know and be able to recognize the first 2. When L equals 0, it's called an s orbital. S orbitals are spherical. So I like to draw them this way. It's supposed to be 3-dimensional, but it's a sphere. Okay, so we have that's the one that looks like a ball. When L equals 1, it's called a p orbital, and p orbitals look like dumbbells. But there's a node in between them where no electron can reside. Okay? D and F are the types of orbitals. So remember, it goes, if L is 0, 1, 2, or 3, it goes S, P, D, F. D and F are much more complicated in shapes, and so I want you to know that they exist, and I want you to know like what electrons reside there, but I wouldn't expect you to be able to draw them. But you should be able to draw both S and P. Alright, so the third quantum number that we come to is called the magnetic quantum number, and it's M sub L. And it describes the 3-dimensional orientation of the orbital. So for example, if we have a sphere or orbital, there's only one orientation. However, if you have the p orbital, there are actually 3 orientations. Let me see if I can draw this very well. In 3 dimensions. Because we have the x, y, and z axis. And so the third one is the one that's the most difficult for me to draw. It would be going away from you. One dumbbells would be going away from you, one would be coming towards you. And so it would look something like that. Okay? And so there are 3 possible P's, and we'll find out there's even more possible D's and more possible F's. the values for m sub L is always going to be from negative L to positive L. So let's do an example. If we go back to our example that we had before, where n was equal to 3, then the possible values for L was 0, 1, and 2. Well, here what we're saying is from negative L, let's say it equal to m sub L, let's say it equal to positive L. So, since L can go all the way up to 2, that means that in this scenario, m sub L could equal negative 2, negative 1, 0, 1, and 2. Those are the possible values for m sub L. Once again, it tells you the three-dimensional shapes. So that lets us know that there are up to 5 different orientations in the d orbital. Okay, we had we only have one possible s, we have 3 possible d's, and then we can have up to 5 possible m sub l's. So, to summarize here, we have 1 possible s orbital, 3 possible p orbitals, 5 possible d orbitals, 7 possible f orbitals, and so on and so forth. Now, the orbitals within the same value of n form what they call a shell, and anything in the different orbital types within that shell are called subshells, or sometimes they refer to them as suborbitals, but they are shells and subshells. And so this table here, please don't memorize it, but just recognize, and you should be able to determine these values just knowing the fact that, for example, n has to be greater than or equal to 0, L has to be between n minus 1 and 0, and m sub L has to be, whoops, let me undo that one. M sub L has to be between negative L and positive L values. So let's look at some of these examples in greater detail. These are what the s orbitals look like. So 1 s orbital is a small sphere, 2s would be a larger sphere, 3s would be an even larger sphere, and you can go to 4, 5, 6, 7s. Okay? An s orbital is whenever you have a value of L equals to 0, and the radius of sphere gets larger and larger as n gets larger. That's where most people can remember, like the whole idea of the bullseye. But in reality, instead of a bullseye, it's sort of like a Tootsie Roll Pop. It's just or a jawbreaker, which is layer upon layer upon layer, concentrically. This is showing the probability maps. And so what we see here is if it's a 1s orbital, you have the highest probability of being within, 1 angstrom or so of the nucleus. And so it looks like a little sphere. Whereas if there's 2s, we still have that 1 for the 1s, but then we have a higher probability of finding electrons in the 2s. And so that's where, to me, it always looks like a jawbreaker or something, gobstopper. 3s, we're going to have 3 possibilities. But if you notice, in each of these, there's a region called a node where there's no possibility of finding an electron. See, because it goes to 0. That one right there goes to 0. P orbitals have 2 lobes with a node in between them. And so that's why, to me, they always look like dumbbells. So we can have them along the x, y, and z axis. The d orbitals, when L is equal to 2, and there are 5 possibilities. You do not need to be able to draw these, but there are 4 of them are the kind that have 4 lobes. And then the 5th one, to me, looks like a donut with a, dumbbell going through it or something, almost, or a pacifier for a baby. But once again, they just have these really odd shapes. Okay. Now, when we work with hydrogen, it's very, very simple because there's only a single electron. So that single electron, I'm going to show it right there, is, and its ground state is always in the 1s orbital. And remember, if we add in an exact amount of energy, we can jump it up to where now it's up in the 2s orbital, or you can go up to the 3s orbital, and so on and so forth. When it comes back down, it would emit that amount of energy. Remember, we have the whole idea from earlier in this chapter that E is equal to h times frequency. So with one electron, all of the orbitals on the same energy level have the exact same energy. And so what I mean by that is, if we look, here the 2s and the 2p orbitals are exactly the same in energy. And so that's got a term called degenerate. Degenerate means that they have the same, they're equal in energy. That's fine and dandy and great, but what happens whenever we start adding in more than one electron? So after helium, helium's going to have 2, but then we got lithium that has 3, and so on and so forth. Then it gets more complicated, because once we start getting more than one electron, since they are both negatively charged, they're going to start to repel each other. They, like charges, repel each other. So as they start to add more and more electrons in these orbitals, they're going to start to repel. So if we look now, and we see, for example, here on the 3rd energy level, we have 3s, which is lower in energy than 3p, which is lower in energy than 3d, because we can get up to 10 electrons on that d orbital, but we can only get 2 on the 3s orbital. So therefore, these, for anything beyond hydrogen, they're going to start to repel each other, and so there's the energy levels are no longer degenerate. They're going to be differences, slight differences in their energies. Then, later on in the 1920s, it was discovered that no two electrons in the same orbital can have the exact same energy. You can imagine them as being like little spheres themselves. This is one electron, and it's just spinning around in one direction. And because of that, it's going to give off a magnetic field, similar to the way that Earth does. And so this one we're calling the North Pole, whereas the other electron in that orbital spins the opposite direction, and it's going to have the opposite magnetic field. And so because of that, that's where the 4th quantum number comes into play. And it's called the spin quantum number, and it's m sub s. And there are only 2 possible values for m sub s. It's either going to be negative 1/2 or positive 1/2. So Pauli then came up with this term, and it's called the Pauli exclusion principle. Okay? And the Pauli exclusion principle says that there are no 2 electrons in the same atom can have exactly the same energy. And that's why in each of the orbitals we can only have a maximum, or each of the subshells, I should say, we can only have a maximum of 2 electrons, because one of them will have a plus 1/2 spin, the other one will have a minus 1/2 spin. Okay, so let's just do a quick review of everything, of the 4 quantum numbers. First, and they go in order, we have the principal quantum number, which was n. N tells you the energy level of the orbital. And n must be an integer, and it has to be greater than or equal to 0. The second one was the angular momentum quantum number, and it has a lowercase l as its symbol. And it gives you an idea of the shape, or it tells you the shape of the orbital. So the possible values for L goes from 0 to L to n minus 1. The third quantum number is the magnetic. It is the magnetic quantum number, m sub L. And it gives you the orientation, the 3-dimensional orientation of that suborbital. And its values can range from negative L to positive L. And then finally, we have the 4th one, which doesn't describe the orbital. It just tells you it's the spin quantum number, and its symbol is m sub s, and m sub s can equal either plus 1/2 or, well, it did not come out right, plus 1/2 or minus 1/2. So let's do an example of the possibilities. All right, let me change color. So let's just say, let's write out all the possibilities for n equals 2. So if n equals 2, L can equal 0 and 1. M sub L can equal -1, 0, and positive 1. And then you can imagine M sub S is that for each one of these, the one that has a -1 can also have a plus 1/2 and a minus 1/2. 0 could have a plus 1/2 and a minus 1/2. The positive 1 M sub L could have one with the spin of plus 1/2 and one with the spin of minus 1/2. So no two electrons in the same atom can have identical sets of quantum numbers. Let's review what we've done in this video and with the last video. So first, we've said that electrons can live in very specific orbitals. These are called energy levels, and they are required to absorb a specific energy amount if they want to jump from one energy level to the next one. Or if they're falling from one energy level to the next one below it, it will emit that specific energy. We also use the de Broglie equation, de Broglie wavelength equation, in order to mathematically solve the wave properties of matter. And then finally, in this video, we've talked about a set of 4 quantum numbers that specifically describe each electron in an atom. It's sort of like the electron's social security number or the electron's address. Hopefully this has helped you understand a little bit more about quantum numbers. And in the next video, we'll go through and we'll start doing what's called electron configurations. I'll see you in class.